Okay, so last time we talked about, I guess, sort of how emissivity is defined and how complicated emissivity can be, given that emitted radiation can depend on direction and wavelength. At the end of last time, we talked about a couple of assumptions that we can make that make solving problems easier. One assumption is that a surface can be diffuse, which means that the emissivity doesn't depend on direction. Right? Every direction you'll have the same emissivity. And gray, which means that emissivity doesn't depend on wavelength. So, across all the wavelengths we have the same emissivity. So today we're going to talk about how you deal with radiation exchange between these diffuse gray surfaces. First we got to talk about what happens to radiation that hits a surface, right? We've talked last time a lot about how a real surface emits radiation, and that's the whole idea behind emissivity. There's a couple other surface properties we need to talk about that are related to what a surface does with the radiation that hits it. So this radiation that hits it, we call that irradiation. We give it the symbol G. So irradiation here is the radiation hitting this surface per unit area. So irradiation, the symbol is G, it has units of watts per meter squared. This irradiation can literally come from anywhere, right? It's stuff that maybe is emitted by other surfaces in the surrounding, or it could be stuff that is reflected off of other surfaces in the surrounding, but for whatever reason it finds itself striking this surface. And once it strikes this surface, one of three things can happen. It can either be reflected from the surface, it can be absorbed by the surface, or it could maybe be transmitted through the surface. And there's a surface property defined to characterize all three of those different possibilities. So reflectivity, and that's given the symbol rho, is the fraction of this irradiation that is reflected off the surface. So the reflected radiation will be rho times G. Absorptivity is given the symbol alpha. That's the fraction that is absorbed. And transmittivity, given the symbol tau, that's the fraction that is transmitted through it. And in general, all of these properties will be, like emissivity, potentially a function of direction and also of wavelength. And in this case, what we mean is the direction that the irradiation is coming from and the wavelength that the irradiation has, right? So that direction and wavelength has everything to do with where are these other surfaces located and what temperatures are they at and what are their emissivities, right? So it's a very complicated situation from that standpoint. Today we're going to restrict ourselves to these diffuse gray surfaces, which means that these properties, reflectivity, absorptivity, and transmittivity, are not functions of direction, and they're also not functions of wavelength, right? So that makes it quite a bit easier. I think it should be obvious that the sum of the reflectivity, absorptivity, and transmittivity has to be equal to 1, right? All of this irradiation has to be either reflected, absorbed, or transmitted. There's no other possibility, so the sum has to be 1. We're only going to talk about opaque surfaces, not transparent or semi-transparent surfaces, and therefore for our surfaces the transmittivity is going to be 0. So that means that the reflectivity plus the absorptivity have to equal 1. And then there's one more thing that makes our life easier, and that's what's called Kirchoff's law. And Kirchoff's law just states that the absorptivity and the emissivity have to be the same. And this actually is true more generally than that. It means that the absorptivity at a given wavelength and direction has to be the same as the emissivity at that same wavelength and direction, right? And that's you can see how that's derived if you look in the book. It's basically kind of a thought experiment where you think about some object that's sitting in a chamber and it's at the same temperature as the chamber, and so basically if it's at a steady state sitting there, then what that means is that how much radiation emits and how much it absorbs has to be the same. And from that, you can sort of convince yourself that the absorptivity and the emissivity have to be the same. So that's what Kirchoff's law says. Basically then, if we get rid of transmittivity, we have three surface properties that we need. We need absorptivity, reflectivity, and emissivity. But we have these two relationships that are between them, right? This one is basically just saying we have an opaque surface, and this one below it is saying that Kirchoff's law is valid. So what that means is that if I give you any one of these three properties, the other two you can calculate. If I give you emissivity, then immediately you know the absorptivity, and you know the reflectivity is 1 minus the absorptivity, which is 1 minus the emissivity. So if I have a highly reflective surface, that means it's a very low emissivity surface, a very low absorptivity surface. All right, so that's the first piece of the puzzle is these different surface characteristics and how they're related to one another. The second piece of the puzzle is actually thinking about what's called radiosity. So we have a surface sitting here. It's being exposed to some irradiation, right, from other places. We talked about that already. It's maybe being heated or cooled in some way. And then we have some of this irradiation that is reflected, and then we also have the surface itself emitting radiation, and that's the how much is emitted. Of course, that'll be the emissivity times the black body emissive power. So the radiosity is how much radiation leaves this surface, right? The radiosity must be composed of however much of this irradiation is reflected, so this is rho times G, and then also how much radiation is emitted by the surface itself, so that's emissivity times the black body emissive power. The sum of those two things is the radiosity, and the reason the radiosity is important is because the radiosity is what goes off and becomes irradiation for all of the other surfaces, right? So the radiosity is going to interact with all the other surfaces in the vicinity in order to become irradiation, and that interaction happens through these surface-to-surface resistances that we talked about last time, right? So this is my equation for the radiosity right here. If I remember that, if I go back one, reflectivity is 1 minus the emissivity, then here's my equation written totally in terms of the emissivity. One thing to recognize here is that when we were talking about black surfaces, I never talked about radiosity. We didn't have to, and the reason is because for a black surface, the radiosity is identical to the black body emissive power, right? If you think about what's going on with the black surface is going to absorb all the irradiation, so this term is going to go away, and then the black surface is going to emit the black body emissive power, so the emissivity is going to be 1. So the radiosity for a black surface is going to be identical to the black body emissive power. And that makes sense if you think about it, right? What's coming off of a black surface and leaving to go interact with all of the other surfaces? Well, it's just the black body emissive power, because that's what's leaving the surface. And you get that if you plug in an emissivity of 1 here, right? An emissivity of 1 corresponds to a black surface. 1 minus 1 is 0. This term goes away, and that term turns into the black body emissive power. So that's our first equation. Our second equation we get just by doing an energy balance on this surface. So an energy balance on this surface says that in has to be equal to out. There is no storage since I'm doing an interface energy balance. The in here is the net radiation heat transfer from the surface, right? This is how much the surface is being externally cooled or heated. So that's Q dot I is coming in. And then the out, the other part of the in is the irradiation times the area. So that's over here. I put it on the other side with a negative sign. And then the out is the radiosity times the area. So that's right here. So this is just an energy balance on the surface. I'm just going to factor out the area. So Q dot is AI times GI minus, JI minus GI. So these are two equations. And what I'm going to do next is try to eliminate G. Right, so what I'd really like is an equation that tells me what is the radiosity leaving a surface that's written only in terms of characteristics about that surface, right? So I want the radiosity in terms of things like the emissivity of the surface and how much it's being heated or cooled, and what its black body emissive power is, right? So that's basically the surface temperature, and what its area is. Because if I have an equation that tells me that, now I'm in business, right? Now I can take that radiosity and I can connect it to all the other surfaces through surface-to-surface resistances, and I can start to look at my surfaces again as sort of this network of radiosities that are interacting with one another. So that's just a little bit of algebra. I'm going to take this equation here, this equation 1, and I'm going to solve it for the thing I want to get rid of, which is G. So I'm solving for G. So J minus epsilon times EB divided by 1 minus epsilon. And I'll take this G equation and substitute it into equation 2 here. So I substitute it right here, and I get this. And then all I'm going to do is take this first term and multiply and divide by 1 minus epsilon sub I, so that it has the same denominator as the second term. So that's what I did here. And then if you just look at the top, I have J minus epsilon sub I times J. And then here I have a minus J, and a minus is a plus epsilon sub I times EB. So this J and this minus J cancel, and I get this equation here. So Q dot, the rate of the net, so this is the net radiation heat transfer from the surface, is equal to A times this quantity here, minus the emissivity times the radiosity, plus the emissivity times the blackbody emissive power, divided by 1 minus the emissivity. So if I factor out the emissivity, I get this term, I get this equation right here. Q dot is equal to this group times EB minus J. So as hoped, as promised, I guess, I get an equation here that gives me the radiosity in terms of things that are pretty convenient for me, right? In terms of how much the net radiation heat transfer is from the surface, Q dot I, and then characteristics of the surface itself. So the emissivity, the area, and this is the temperature, right? This is sigma T to the 4th. And if you look at this equation for a second, it looks again like a resistance equation, right? I have Q dot from the surface is being driven by the difference between the black body emissive power of the surface minus the radiosity, which is what actually comes off of the surface. And then the inverse of this must be the resistance, and we call this the surface resistance. So here's how I represent this as a resistor, right? I have EB minus J, and then there's my surface resistance, has the same units as my surface-to-surface resistance, right? This is units of 1 over meter squared, and that gives me my Q dot. Just to be clear, every surface then is going to be represented by a node, and the node is going to be at a potential that's equal to EBI. So even though the surface may not be a black surface, its potential is EBI. But this EBI, this black body emissive power, this is not the radiosity. This is not the stuff that goes off to interact with other surfaces, right? To get to the radiosity, I have to go through this surface resistance to get to J. This J is the radiosity from the surface. This is what goes off and interacts with the radiosity from all of the other surfaces. So all we've really done then is, we've made our radiation resistance networks a little bit more complicated. So here's what I had before. I had 3 surfaces, 1, 2, 3, that formed an enclosure. Before we made the assumption that all of these surfaces were black, right? So epsilon 1, epsilon 2, and epsilon 3 were all 1. And that gave me a resistance network that looks like this, right? The resistance network was that EB2, EB1 is the potential of this surface, EB2 this surface, and EB3 is this surface. And we have these surface-to-surface resistances that connect these different surfaces, right? And basically, we didn't talk about it, but the assumption that I was making is that because these surfaces are black, these black body emissive powers are identical to the radiosities, right? And that's why they can be connected together. These radiosities are what should be connected together, right? So this was the network we had before. If I have the situation where these surfaces are no longer black, so these emissivities are not 1, then this network goes away. And the reason it's not any good anymore is because right here, that assumption isn't any good anymore. The black body emissive power is no longer equal to the radiosity, and therefore I cannot connect black body emissive powers together the way I have. I can still connect these radiosities together, but I need another resistance that takes me from the black body emissive power to the radiosity.